Hi everyone. So the purpose of this video that Tim and I are making is to give you a general idea of how to design your presentation. Now hopefully you will finish up your experimental work at the end of the second day of the project, and when you come in the third day of the project you will be able to work on your presentation. During the first half of class, you will have time to work on your presentation. And during the second half of class, you will actually give your presentations in front of the TA, and then they can give you some advice about how to fix the presentation. So you should have plenty of class time in order to do this. If there are a few final experimental things that you need to do in order to complete your project on day 3, that's fine, and you can do those, and everybody should bring their PPE or goggles and stuff, lab coats, just in case there are some people who do need to work on actual chemistry stuff just to finalize their project. But the idea is, and hopefully this will work out for you, that you could have that last day to the third day to work on your presentation, and then the fourth day you'll actually give the real presentation. So this presentation that we're giving is designed to help you with that presentation, and what you're going to find is we actually go through all of the stuff, so you can use this as a guideline for how you want to develop your own. So your presentation should be split into 5 parts. One for each of the 4 sections of your experimental work, so the absorbance, the conductivity, the freezing point depression, and the titration parts. And then the 5th section should cover your conclusions, such as what are your recommendations to the New York DEC about whether or not this company is or isn't outside of the guidelines provided. Each of the 4 experimental sections should include the following: an introduction, so give some introduction to the technique that you used, and we'll go through each section and give our introduction. Slide 2 should be the experimental part, and what you did, what did you measure, how did you measure it, so on and so forth, why you did it, what was the reason for your measurements of the things that you chose. So, and again, we'll go through all of this. And then the third slide, that's the data and analysis. What did you get? What did you find out? What does your calibration curve look like, for example? And an explanation of the results. So that's basically that. Then finally, you'll have probably just one slide that is the 5th section covering your conclusion, which is a summary of all of your findings and your recommendation to the New York DEC. Now, this is a couple things that we want to point out, okay? One, our presentation is different from yours in that we're using rhodium-2 acetate as our example. So all of the numbers that we're using are for rhodium-2 acetate. We didn't actually use rhodium-2 acetate. Rhodium-2 acetate is about several $1,000s a gram. So we're not going to actually use that, but the point here is that the numbers are made up, and if your numbers should not match our numbers, okay? That's not they're just for example purposes. They're not for yours should be like ours. Our presentation contains very few pictures. However, you can feel free to use pictures of actual pictures you took of your experimentation, but if you didn't, you could use other pictures you found on the internet that illustrate something that you want to show. So feel free to use pictures to make your presentation look better than ours does. And then the final thing, which is probably the most important thing here, okay? You can't copy our presentation. So we may talk about Beer's Law, for example, and we have specific verbiage that we use for Beer's Law. You cannot use our verbiage. How do you do this? What is a practical way to just not use our wording? Well, one thing that isn't a good practical way is to simply change a word or two, okay? Changing a word or two in the sentence, making something into plural instead of singular, or vice versa, that's not changing the wording. Instead, what you might want to do is write down the concept. So, for example, you watch our video and you say, okay, we explain what absorbance is. So you would write down absorbance. Then come back, a day later or whatever, and write in your own words what absorbance means to you, so that you're not tempted to copy the wording that we used. So basically, if I were doing this, I would write down the concepts that are conveyed and in very short number of words, and then come back later and explain those concepts in my own words, so that I'm sure that I'm not copying the presentation that's given. All right, so that gives you a general idea of what we are doing here in our presentation. And now Tim and I will go through exactly what is expected of you. But again, we're using rhodium-2 acetate as our example. So I'm going to turn it over to Tim, who will start with the spectroscopy section.
So Colin and I performed this project using rhodium-2 acetate, and we're now going to present to you what we did during this project and what our findings were as a result of the experimental methods that we explored. So the first section for us is the absorbance. Now, absorbance, as an idea, is essentially the measurement of the amount of light absorbed by a sample. The light is absorbed by the sample because the photons hit the electrons in the sample. Those electrons are excited by the photons and transition to a higher energy level. And what that does is it absorbs the light, so now there is some of the light that's hitting the sample not making it back to our eyes, or in this case the spectrophotometer. So we can see where each of our samples absorbs an amount of light. Now, absorbance allows us to measure the concentration because as there's more material in a solution, the absorbance increases because, simply put, there's more stuff to absorb the light. So as you increase the amount of solute in your solution, you're going to increase the absorbance because more solute is available to absorb that light. So we're going to be looking for a range in which the concentration and the absorbance are proportional or linear with respect to one another. And in this case, that range is going to be over 0.1 to 1 absorbance units. Lastly, I just want to mention that a spectrophotometer uses a blank sample in order to determine the amount of light that's absorbed when nothing is absorbing light. So in this case, we used water as our blank. So when we performed this part of the experiment, we used water to give the instrument an idea of how much light is absorbed when there's nothing absorbing light. So that way, any small inconsistencies based on the vial we're using or the spectrophotometer we're using are taken into account because we can subtract that amount out of each of our solutions once we had our solute in the spectrophotometer. So specifically for us, we were measuring the absorbance of rhodium-2 acetate. We found that the lambda max was 415 nanometers for both the known and unknown solutions, and the fact that the lambda max is the same for both the unknown and the lake water solution, or rather the known solution and the lake water solution, indicates that both of them contain rhodium acetate. We know that the solution we made did, so the fact that the lake water has the same lambda max indicates that it's likely the same material. We found the linear range by measuring the provided solution and diluting it until the concentration was on our linear range between 0.1 and 1. Once we did that, we, in triplicate, made 5 standard solutions using parallel dilution, and they covered a range of around 22 to 5.5 millimolal. Once we had the absorbance of each of those 5 standard solutions, we made a calibration curve using the average values, and we found that the standard solutions on our particular curve had a range from 1.01 to 0.22. Now you'll notice that our range covers 1.0 to 0.2, while our linear range is 1.0 to 0.1. And it's mostly okay that we didn't cover the 0.2 to 0.1 range, because that's only a small fraction of the total linear range. The important thing is that our values covered 90% of our linear range. Had our values only covered 0.2 to 0.25, that would have been too small of a range, and we would have needed to remake our measurements. So here are our results from the absorbance portion of the experiment. You can see our concentrations of our solutions that we made here, along with the absorbance of those solutions on our first trial, our second trial, and our third trial, along with the averages of those absorbance. And then here we have graphed on the x-axis the concentrations that we used, and on the y-axis the average absorbances. And you'll see that our R squared was 0.997, which indicates that we did a good job making our solutions and have a good linear relationship between concentration and absorbance. We then took the lake water sample and we measured its absorbance 3 times, and we found the average absorbance to be 0.2544. Once we did that, we actually plugged in the absorbance into our y value and solved for x and determined that the concentration of the lake water was 0.00626. It is possible that our values were off slightly based on the fact that we blanked with water, and we know that the lake water solution also contained acetic acid. So our solutions may have actually been slightly off, and it perhaps would have gone better had we made our solutions in acetic acid and blanked using acetic acid as well. So that about wraps up our absorbance section of the experiment, where we were able to find that the concentration was 0.00626 molal. Next, I'm going to talk about the conductivity portion of the experiment. The conductivity portion of the experiment was performed using conductivity probes. And a conductivity probe essentially measures the amount of current that's being carried through a solution. So a solution that has a strong ability to carry a current will measure a high conductivity, and a solution that has a weak ability to carry a current will have a low conductivity. In our case, we're using electrolytes, which are substances that conduct current in solution. Generally speaking, they are ionic compounds that dissociate into their ions in solution. So in this case, when we had our rhodium acetate, whose formula is given here, it dissolves in water into rhodium 2 plus and 2 acetate ions. So rhodium 2 acetate is an electrolyte because it's an ionic compound that in solution dissolves into 2 ions, which are then able to conduct electricity in that solution. So similarly to absorbance, as the concentration increases, the conductivity increases. This is because, again, there's simply more solute in the sample. In this case, it's not that the increased solute is allowing light to be absorbed, but in this case it's because the increased amount of solute simply is able to carry more current. Each mole, or millimole in this case, of solute that is added to the solution is able to carry the current. So more of the solute in the solution means that more current can be carried and a higher conductivity will be measured. So because the concentration and conductivity increase relative to one another, we expect to find a linear relationship over a broad range, and in this case we're going to be exploring the range of 300 to 2000 microsiemens per centimeter. So we're going to make a calibration curve over that range, which will allow us to measure the conductivity of the unknown solution, and use our calibration curve to back calculate the concentration of that unknown lake water solution. So what we did was we took the provided solution, we measured the conductivity, and it was well above the upper limit of 2000 microsiemens per centimeter. So we diluted the solution until the conductivity was measured to be 1540 microsiemens per centimeter. Once we had that solution's concentration and conductivity measured, we were able to calculate what concentration should have a conductivity around 2000 microsiemens per centimeter, and then we were able to make our curve using 5 solutions with conductivities between 2000 and 300 microsiemens per centimeter. So we made those solutions in triplicate, starting from the provided stock solution each time, and measured their conductivities. The concentrations and conductivities of those solutions were then plotted on a calibration curve, and we used that to determine the concentration of the rhodium 2 acetate in the unknown lake water solution. Just like in the absorbance section of the experiment, we used the average values to plot our graph. So you'll see on our data page here that we have the concentrations of our solutions, as well as the conductivities on trial 1, 2, and 3, and then our average conductivity, which we've graphed versus concentration here on our curve. You'll see we actually have this measure labeled incorrectly. It's actually our conductivity in microsiemens per centimeter. So we have our trials here, and you'll notice they cover a range of 2,100 or 2,200 to around 500, and that doesn't cover the entire range of 2,000 to 300. In fact, it goes a little above it and doesn't quite make it to the bottom. But again, just like the absorbance section, that's okay, because while we didn't cover the entire section, we did cover the portion of the curve that our lake water sample measured on, and we covered about 90% of the total range that we needed to cover. So while we didn't cover everything, it is an acceptable range to have covered. We didn't only cover a range of 200 microsiemens per centimeter. We didn't measure well above or below the range, but we did cover most of the range. So when we took our lake water sample, we measured its conductivity 3 times, and the average conductivity was 674 microsiemens per centimeter. Just like last time, we plugged that in as the Y value on our calibration curve and solved for X, our concentration, and found that the concentration of the rhodium-2 acetate in the original lake water sample was 0.00724 molal. Again, a possible error in this is that there is another weak electrolyte, the acetic acid, present in the solution, which may make the unknown more conductive, so it's possible that our unknown has an inflated conductivity that is not due the solely to the rhodium-2 acetate, which our calibration curve was based solely off of rhodium-2 acetate. Additionally, the lake water is likely to have more ions in the water itself than DI water that we used in the lab to make the calibration curve. So both of these things could have contributed to giving us an artificially inflated concentration of the rhodium-2 acetate based on our calibration curve. So now, I'm going to take a break from presenting the actual solution, and we're going to discuss something relative to your absorbance and conductivity concentrations. So, when you're performing this experiment and you're doing the project, you may find that your concentrations based on your absorbance and conductivity are either very similar or very different. So, if the two concentrations are different, you'll need to include a slide like this one, where it says the molality of the solution was determined to be whatever you determined it to be, based on either the conductivity or the absorbance data. But the question you need to ask yourself is, why would you choose the conductivity data or the absorbance data over the other one? And that's not a question I'm going to answer for you right now. It's something I'm going to leave for you to think about and come up with a reason that you're more than welcome to discuss with your TA before giving your presentation, as kind of a thought experiment to try and figure out why you think one or the other is correct. There's no strictly correct answer in this case. The important thing is that you think about it and come up with a scientific reason why you would choose one or the other. The other option is if you check your concentrations or calculate your concentrations based on absorbance and conductivity, and you find that the average molalities are very close. In that case, you'll need a slide where you say that you took the average molalities of those two very similar numbers, and the average molality of the solution is whatever it is going forward. The reason you need to include a slide which specifically states what concentration you're going to use is kind of threefold. One, you need a molality for your freezing point depression. Two, you need a concentration to use for your Henderson-Hasselbalch equation in the titration portion of the experiment. And three, you need a concentration of your acetate salt to report back to the NYDEC in your conclusion to determine whether or not the company may or may not be operating outside the allowed constraints placed on them by the NYDEC. So you need to include a slide that specifically states which absorbance or what absorbance you're going to be using moving forward through the rest of the project. So, having said that, we're going to move back into the presentation with the freezing point depression, which I'm going to turn it back over to Colin for him to start on.
So in this section of the experiment, we took a look at the freezing point depression of our solution, of a known solution, and our unknown lake water sample in order to determine if they had the same Van't Hoff factor, and if that Van't Hoff factor was close to the theoretical Van't Hoff factor of rhodium acetate dissolving in solution, which gives you rhodium 2 plus and the acetate 2 acetate ions, so it's 3. So that was our goal. Freezing point depression is a colligative property. So that means that the degree of change depends on the number of particles in solution, but not on the specific identity of those particles. In our unknown lake water solution, rhodium 2 acetate and acetic acid were present. In our known solution, we simply had rhodium 2 acetate in water. The freezing point depression is related to the Van't Hoff factor as follows: delta T of freezing equals I times Kf, a constant, which is 1.86 degrees C per molal, times the molality. And in our case, we decided to use the molality from the spectroscopy part of the experiment to plug into this equation. So as we look at the freezing point depression, and in fact, in terms of our actual measurements, we measured the freezing point of 5 milliliters of lake water and 5 milliliters of the solution that was provided in class, which contained 0.5 grams in 100 milliliters of solution. Each solution was frozen in triplicate using an ice salt bath, and we used a thermometer to monitor the temperature, and we used Microlab to do that. So we had time on our x-axis, we had temperature on our y-axis, and we monitored the temperature through time until the solution froze. What we found was for the lake water sample, we had these freezing points and an average of minus 0.02. Using this, the experimental Hoff factor was 1.7. For 0.04892 grams of rhodium acetate, rhodium 2 acetate in 5 grams of water, we had these freezing points, and this was our average, and we found the experimental Hoff factor to be 1.7. The theoretical Hoff factor is 3. So the experimental Van Hoff factor for the lake water sample and for the known solution were similar, again indicating that our solution likely contains rhodium 2 acetate. They're not super similar to the theoretical Van Hoff factor, but that's not uncommon. So therefore, we're going to assume that this contains rhodium 2 acetate. Now, I'm going to go off of the script a little bit here in terms of, I'm not going to talk about the slides directly for a minute. When we look at this would not be necessarily part of my presentation, is basically what I'm saying. When I look at this, if you look at these freezing points, they're extremely close to 0 for both cases, which may mean we end up with some erroneous data. And it may not be possible to calculate experimental Van Hoff factors when these are such small numbers. So even a 1 degree temperature change will cause a huge fluctuation in the experimental Van Hoff factor. Keep in mind, you're not going to get experimental Van Hoff factors of thousands or something like that, but they may not be super close to each other just from small deviations in the thermometer, in the placement of the thermometer, in the calibration of the thermometer, or whatever. The temperature changes simply aren't big enough. This can be looked at as a disadvantage or a poor experimental design. However, that's something you could talk about in a presentation. Freezing point depression of dilute solutions is probably not the best experimental procedure to use to verify whether or not you have a certain solute in solution. So I think that that's the overall overarching message here, and it's important that if that's what you find, that you mention that, and it's not wrong for experiments to fail. It's important that when experiments do fail, we talk about why they failed, and learning and understanding why they failed is kind of the point here. All right, so that is me going off of the actual presentation and not something that I would expect you guys to say during the presentation or would want you to say during the presentation other than the conclusion. But now I'm going to go back to the presentation and talk about pH by titration. So pH is a measurement of the concentration of H3O plus hydronium ions in solution. Specifically, it's the negative log of the concentration of the hydronium ion. So in this case, we're going to determine the concentration of acetic acid by titration using sodium hydroxide solution. We are going to standardize the sodium hydroxide before we do this titration with KHP, potassium hydrogen phthalate, according to this reaction. Then we're going to determine the pH using the Henderson-Hasselbalch equation. So when we look here, the first thing we did was we standardized the sodium hydroxide over 3 trials using KHP and phenolphthalein as an indicator. All titrations were performed in triplicate, and we found low relative standard deviations, which meant that our titrations were done precisely. We have a typo here. The acetate concentration was found using spectroscopy in our case, and since the rhodium 2 acetate contains 2 acetates, we did have to double that concentration. So essentially what we're doing is we're using the Henderson-Hasselbalch equation, where pH equals pKa, which we looked up as 4.75 or 4.76, plus the log of conjugate base, this is acetate ion, which is double the concentration from the spectroscopy section in our case, over the concentration of the acid, which is what we found using our titration. On the next slide, I have the actual titration data. We used about 2 milliliters of NaOH over 3 trials. This gave us the moles of acetic acid. The average concentration of NaOH was from our standardization, and we had a low RSD there, so we just used the average concentration. We found the moles of acetic acid, and then finally the concentration of acetic acid in the 5 milliliters that we titrated. The average concentration was 0.0408 molar, and the RSD was 16, indicating, or about 17, indicating that our data was relatively precise. We used the average concentration of acetic acid and the Henderson-Hasselbalch equation, as described previously, to predict that the pH was 3.93. And we did this using our spectroscopy concentration. The pH probe read 3.14. The difference between the measured pH and the theoretical pH could be because of other materials in solution causing an artificially low pH. pH meter is essentially a conductivity meter that is specific to hydrogen ions. If you have a lot of other ions in solution, it can throw off pH readings, and that's not something I want to get into in too much detail here, but pH meters aren't always super accurate in solutions with lots of ions. There could also be some error in our titrations, but our RSDs were low, so they're probably they're certainly precise, and they are probably fairly accurate. So this is basically the pH by titration. The last thing that we want to do is we want to draw a conclusion reporting to the NYDEC, which I'm going to turn over to Tim to do so. One thing I do want to mention here is that the volume of NaOH used is very, very small, right? Only 2 milliliters. This can cause errors in your titrations because one drop is a much greater percentage of a few milliliters than it is of 15 or 20 milliliters. Furthermore, if you're more than a drop off, that's even more of a greater effect. So having such a small volume of NaOH really puts a burden on the experimental procedure to get a low RSD. You have to be really careful and make sure that exact last drop gets the solution to turn pink in order to keep your RSDs low. All right, now I'm going to turn it over to Tim, who's going to talk about the conclusion.
So, in conclusion, I have listed here the given NYDEC maximum concentration, the expected Van Hoff factor, and the acceptable pH range, again given by the NYDEC, and I have them compared to our calculated concentration, our experimental Van Hoff factor, and our measured pH. So the experimental Van Hoff factor, while different from the expected Van Hoff factor, as previously stated, was the same for both the lake water solution and the solution known to contain rhodium-2 acetate. So because of that, and the fact that both the rhodium-2 acetate and the lake water sample had lambda maxes of 415 nanometers, it's fairly likely that the solution does in fact contain rhodium-2 acetate. Additionally, when looking at the maximum allowable concentration of the rhodium-2 acetate, the maximum was 0.004 molal, or 4 millimolal, and by absorbance we found it to be 0.0062, or 6.2 molal, and by conductivity we found it to be 0.00724 molal, or 7.24 molal. In either case, though we chose to use the absorbance concentration, the concentration of rhodium was higher than the allowable NYDEC limit. Additionally, when looking at the pH, we found that the allowable pH given by the NYDC was 4 to 9, and when we calculated the pH, we thought it would be 3.93, but using the pH probe, we found it was even lower than that, 3.14, both of which, again, are lower than the limit range allowed by the NYDC. So based on the data that we collected in this project, it is our recommendation to the NYDC that the company may be polluting the water with materials other than those allowed, or they may be polluting in concentrations higher than they were given permission to do so. So in either case, the NYDC should continue their investigation into this lake water, as we believe there may be something inappropriate going on with their waste disposal. So that brings us to the end of our presentation, and we hope that that helps you as students figure out how to perform your presentation. So before we end the video, I'd like to cover a few things, a few tips that we would like you to keep in mind while doing your presentation. The first one is, again, as said at the beginning of the video, do not copy the material that we put in this presentation. It's fine to use it as inspiration, and the overall construction of our presentation, you're more than welcome to copy with regards to spending 3 slides on each subject, putting the subjects in order, a conclusion at the end, what's on the slides itself, however, you should not copy. So don't take our exact wording, don't take our wording changed only by a couple of words. We recommend that you do, as Colin said at the beginning of the video, that maybe you watch the video, take some very generic notes, and then the next day come back to it, your notes, and use those notes to write your slides. Doing it that way, it's very unlikely that you'll end up writing something that's extremely similar to our information. That said, we don't want you to think that we're trying to catch you in a trap here, because we understand that your wording and your data will be, of course, similar to ours. The idea is that it's not exactly copied and that everything you do is your own original work. When giving the presentation, you should make sure that everyone in your group has an opportunity to talk. So part of the purpose of this project is actually to give you this opportunity to do a presentation. So in this case, you're presenting some material that the people around you are familiar with. The people around you are about to also present on very similar material, and everyone's kind of in the same boat. So it's a relatively low pressure environment to give a presentation. So this can be time for each of you to practice giving a presentation, doing things like making eye contact with your audience as a whole, not focusing on one person, not reading from the slides, giving everybody ample opportunity to speak. These things are important when you're giving a presentation, and regardless of what your career choice is, it's relatively likely that at some point you're going to have to get up in front of a group of people and talk to them. So this is a good opportunity to practice the skills that you'll be using later when you need to do that in maybe a more important situation. The entire presentation should take around 15 minutes. Our presentation was a little longer than that, but we also tend to talk longer than most people, as well as in the middle of it we took some time to sidetrack a little bit and give you advice about making your presentation. So for your presentation, it's recommended that you take around 15 minutes to do your presentation, after which your TA and classmates will be able to ask you questions before the end of your presentation. So, additionally, we want you to make sure that you're aware that you have the ability to, and we strongly recommend you use, outside of lab time to work on your presentation. While we do give you the time the third week in order to work on your presentation, you're also going to be giving your practice presentation that week and getting feedback from your TA. And after you give your practice presentation and your TA gives you feedback, other students will be doing it as well, and it's rude not to give them the same attention they gave you, so there's not really a lot of time in lab at that point to change your presentation. So what you'll need to do is meet with your group outside of lab, or alternatively, you'll need to talk about how you're going to split up the work. However you choose to do it is fine, but you'll probably need to work on the presentation outside of lab time in order to get it finished. The last thing I want to point out is that before you give your presentations on the fourth week, you will be evaluating each other on the work that you've done on this experiment. So for the project, there are 4 letter grades. One of them is for your report. One of them is for your accuracy and precision, how well you do making your solutions and your calibration curves. One of them is for your presentation, and all 3 of those sections will be graded as a whole. Every group member will get the same grade for each of those 3 sections. The fourth and final section of the grade will be your peer evaluation, and that will not necessarily be the same for everyone in your group. Before you give your presentation, everyone will be given time to fill out an evaluation form for each of their group members, on which you will be asked to give each of your group members a letter grade. And everyone's letter grade for this portion of the experiment will be based on the average letter grade that their lab partners choose to give them. So it's important that you're an active participant with your group, that you're doing your best to help both with the experimental and presentation, so that when it comes time for your lab mates to evaluate you, everyone is happy and willing to give each other the grade that each of you deserves. So, we hope that all of this information helps you out and makes it easier for you to give your presentation in the lab, and we look forward to seeing some of your presentations during the fourth week of the project.